Okay, what's up everybody? Welcome back. Today we're talking about products. Oops, got my tablet wrong. Products and quotients of vector spaces. So these are two ways that we can take some vector spaces, put them together, make some new stuff, or take a big vector space, pull it apart, make some smaller new stuff. Basically, it's ways of breaking apart and putting together vector spaces. All right. We've recently talked a little bit about matrices, about how to see things in terms of lists. That is, we've gotten back to the old classic kind of vector story. We related things back there. Now, let's try to understand what we can learn a little bit more from that. That is, it's really easy to see how Fn and say like Fm are related to each other. Say if n is bigger than m, then it's like Fm just had a few new things added to it. So this is that basic idea. Essentially what we're going to do is we're just going to say, hey, the same way I built n copies of a field, Fn, just by taking lists of field elements, can I just do the same thing with vector spaces? And the answer is yeah. So here's the definition. The product of vector spaces. So if you have v1 through vm, some vector spaces all over the same field, then the product is just the set of all lists of vectors v1 through vm, where v1 is in big V1, the first vector space, v2 is in the second vector space, and all the way down to the mth vector is in the mth vector space. All right, each thing is in each one. Cool. If you are looking at this, you maybe start to see a parallel, by the way. You might see a little bit of a parallel to, say, some kind of a sum of subspaces, right? Where you're writing a sum where each thing belongs to the corresponding vector space. There's some similarity here, except instead of putting pluses in between things, we're putting commas in between things. So keep that in the back of your mind. There's a connection. All right, addition. How do we do addition here? Well, we'll do it in the absolutely most obvious way possible. That is, we'll take a list of vectors and a list of vectors, and we'll add them together by adding each component in the list. Since u1 in this case would be in v1 and little v1 would be in v1 as well, then u1 plus v1 would also be well defined in v1. Okay, cool. So nothing breaks here. Easy. Scalar multiplication, exact same business. Take lambda, scale the list of vectors, just scale each one. This is the place where having the same field is important. So if lambda is in F, then we need to be able to scale each one of these guys by something in F. That is, they all have to be vector spaces over the same field. All right, cool. So we've got a product. Just, if you've got one vector space, you got another vector space, you can do addition and scaling in each of them. Why not just do it at the same time? That's exactly what this is. So do we get a vector space out of it? Yes. Spoiler alert, yes. So if you have v1 through vm as vector spaces over a common field F, then their product, v1 times all the way down through vm, this is also a vector space over the same field. Okay, cool. I'm not going to prove this one because the proof is essentially exactly the same as something that we've done before. That is, this is the same business as what we did in like the first homework when we tried to understand how to write, say, like, when we confirmed that Fm was a vector space, or when we showed that the set of functions from a set S to a vector space V is a vector space, basically the exact same thing. That is, all we're really doing here, if you want to think about it, is that each of these things, it takes a number and it spits out a corresponding vector in some vector space. Okay. Basically, it's the same example. So this is basically a proof that we've already done before. I won't belabor the point. It is not too terrible. And hopefully, it is pretty clear that if each one of these things is a vector space, then since all we're doing is just doing addition in each one of them and scaling in each one of them, then this list of things is still a vector space as well. All right, cool. But what about its dimension? We've been talking a lot about dimension, this number associated to vector spaces. I'm going to make a claim. So let's suppose that v1 through vm are finite dimensional vector spaces. Then the claim is that their product is finite dimensional, and the dimension of the product is the sum of the dimensions. Okay, interesting. Let's try it. So, how do we prove this? What is your first intuition? I think the easiest way is just to straight up construct a basis. So let's construct a basis for v1 times ... all the way down to vm for this product. Okay. Now I'll need to do a little bit of messy notation. So I'll want to take a basis for each one of these finite dimensional vector spaces. Now there's m of them. I don't want to use a bunch of different letters. So I'm just going to use v. So let v, I will say 1, comma, k, all the way through v n k, comma, k, be a basis for vk, where dim vk is then equal to nk, since that's the length of a basis. Okay. Now, here's what we'll do. Basically, we take the following. So this is going to look messy. Okay, here's the idea. Now, in the first entry, we'll do v1k, and then I'll do the additive identity for everything else. And then I'll go comma, and I'll go all the way down. And then I'll go down to v... oh, sorry, I shouldn't... made one tiny mistake right there. I said v1k when I should have started with v1, 1, just to be clear. Down to vn1, comma 1. And then 0 is all for the rest of it. So that is, I made the lists in the product where the first entry was a basis vector from the first vector space. And then I did this for each basis vector in a basis for the first vector space. Now I will do the same thing for the next one. Okay. And so I will go, okay, and I'll take 0 and I'll take v, let's see, let me make sure I got this right. I got 1, 2, 0, all the way down through the end. And then ... all the way down through. Now it'll be 0, v, n2, comma 2, 0, all the way down through the end. Comma, and then I'm going to write ... all the way down through, and now we'll do this in the very last one. I'm not going to write the whole chunk over again, but I'll just do 0, comma, ... all the way down to a 0, comma, v, n, m, m. Okay, that is, i.e., take the list of vectors in v1 times vm, all the way down through vm, where everything is 0 except for one component, which is a basis, or which is, I will say, which is a vector in a basis of the corresponding space. Okay. Now, since I can write little vk in big vk, since this can be written uniquely as little vk is equal to a 1v1k plus dot 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 all the way down to a nk v nk k. That is a linear combination of the corresponding basis for vk. Then zero comma zero all the way down to zero, then little vk, 0 in the product. So that is, take the corresponding element in the product, which has that vector only, can be written as a linear combo of, and I'm just going to draw an arrow, of this whole big thing right here. This thing. Do you see why? Well, every other element is 0, so anything that has stuff in the other elements, we have to put a 0 next to. All right. And then for vk, we just take the corresponding entries where the vik's, the basis for the vk entries are, and add them with the corresponding scalars. We can write now every v1 through vm, little v's here, in the product as a, I'll say even instead of as, I'll say uniquely as a linear combo of that. Okay. By breaking them apart into a sum. That is, I will write it out. So this you could write as v1 comma 0 and then zeros for everything else, plus dot 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 all the way down through zeros everywhere, and then vm. Okay, so each one of those can be written uniquely. Whole thing can be written uniquely. Nice. Hence, the dimension of the product, that's an x, is the sum of the dimensions of the vi's. That is, so each one of these, notice there are here dim v1 things. Here there are dim v2 things, and so on. That is, if you add it all up, it's the dimension of v1 plus the dimension of v2 all the way down through the dimension of vm. That's how many things are in this list. This is a basis. Okay, so the length of a basis is the dimension. Nice. We've got our result. The dimension of the product is the sum of the dimensions. Sweet. Let's keep going. Okay, so remember that I said there was some kind of a connection going on here between sums of subspaces and this product operation. So let's start to spell it out. So let's suppose that v1 through vm are subspaces of a vector space V. This means that they are vector spaces in their own right, so we can take their product. We can take a linear map, let's call it gamma, capital gamma, that takes the product to the sum by just replacing those commas with pluses. See? Okay. Here's the claim. This sum, the sum of v1 through vm, is direct if and only if gamma is injective. Proof. Let's do it. All right. So if gamma is injective, then gamma of V1 through Vm is equal to 0 if it's equal to 0, then this implies, I'll just write it in the short form, that V1 through Vm is equal to 0, since sending 0 through there gives you 0. And injectivity means that if gamma of V1 through Vm equals gamma of U1 through Um, then V1 through Vm equals U1 through Um. So since sending 0 through gives you 0, then anything else that you send through to get 0 must have been 0. Okay. So the only way to write 0 as a sum of the form V1 plus ... Vm equals 0 with Vk in big Vk is V1 equals ... all the way down to Vm equals 0, which says V1 plus ... all the way down to Vm is direct. Oh, okay, so if gamma is injective, it's direct. Nice. Okay. Now, if gamma, I'll say if the sum is direct, then gamma must be injective, since directness implies that V1 plus ... all the way down through Vm equals 0 for Vk in big Vk, since directness implies that having this means that V1, or sorry, not plus, V1 equals V2 all the way down through Vm, and all of those are 0. So null gamma is just 0, and gamma is injective. Hey, cool. All right. So the injectivity of the map that replaces the commas with pluses is equivalent to the directness of this sum. Pretty neat. What about surjectivity? Let's do something there. Okay, so let's suppose that V is finite dimensional and V1 through Vm are subspaces of V yet again. Then this sum, the sum of V1 through Vm, is direct if and only if the dimension of V1 through Vm is equal to the sum of the dimensions. Oh, okay, cool. Very nice. All right. So, proof. First off, let's notice something. Note that gamma from the previous theorem, okay, is surjective, right? Think about it for a second. Anything that's in the sum of V1 through Vm can be written in this form. Every possible sum like that, we can write just from something here by replacing the commas with pluses. It is, I think, so obvious that if it seemed weird, you just have to think about it for a moment more. This is a, proof by consideration, right? All we're doing is replacing commas with pluses. So there's nothing stopping us from writing anything we can write with pluses with commas. Just switch the commas into pluses or pluses into commas. Okay, so it's surjective. By the fundamental theorem of linear maps, we now know gamma is injective if and only if the dimension of V1 plus dot 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 all the way down through Vm is equal to the dimension of V1 times dot 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 all the way down Vm. Okay, cool. Why is this? Well, gamma, think about it. Gamma sends this product to this sum. Okay, let's spell it out. So, since the dimension of the product is equal to the dimension of the null space of gamma plus the dimension of the range of gamma, that is dim V for a map from V to W, is equal to dim null, whatever that map is, dim range, whatever that map is. That sum. Okay, cool. So we got it right there, which in this case, it is surjective. So this is dim null gamma plus dim V1 plus dot 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 Vm. Okay, so that's the little parenthetical reason why. Notice, injectivity would mean that this null space has dimension 0, since gamma is linear. That gives us that this condition must hold. Okay. Now, by the previous result, I will say, maybe I shouldn't say if, I should just say gamma is injective if and only if V1 plus dot 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 Vm is direct. Okay. So since the dimension of V1 times dot 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 all the way down through, is it times again, Vm is equal to the sum of the dimensions, that is the thing that we proved right here, this one. Okay, so dimension of the product is equal to the sum of dimensions. We have the dimension of the sum is equal to the sum of the dimensions Vm if and only if this sum is direct. Ha! Nice! So this is a direct sum if and only if the sum of the subspaces has dimension equal to the sum of the dimensions of the subspaces. Cool. All right, neat. We got that using products, even though products don't appear anywhere in here. So notice, no products. We just used them as an intermediate step to get to this result about sums of subspaces. Very cool. Direct sums and products are tied together, and you can use this to prove things that don't involve the product. Kind of nice. Let's keep going. Okay, up next, we're talking about how to break down a vector space. Couple of ideas. I think it's a lot easier if you see this with some visualization. So first off, quotient spaces. The first thing we're going to need is the notation of a translate. So for a vector v and v, and u, a subset of v, we're going to write v plus u to be the subset of v defined as v plus any u in u. Here's the idea of it. Here's a visualization of what we're talking about. So here, let's just think of it like this. I will imagine everything is living in R2, say. All right. So I'm going to draw, ooh, I can even use my line tool to make my lines extra nice. Okay, I'm going to take 2 copies of R2, and I'm going to try to show how this works in an intuitive visual way. So first off, I will draw a subset. Okay. So I'm going to take some kind of like a little squiggly ball here. Okay. Now, the idea of it is that I can grab instead now, let me see if I can make this look a little bit nicer. Something like over here. Okay, I'll grab a little vector, say v right here, and this here will be my u. Now, I just imagine moving everything in u by that v. So, I will redraw my little v over here. My little v is right there. Okay. And now, imagine basically taking this guy u here and dragging it over. So let's see if I can kind of redraw u nicely. I should have chosen a shape that was less squiggly, but essentially the idea of it let's see, this is a terrible redraw. So this is v plus u. That is, I took u and I shifted it over by v. Get it? Right? Like this point was right here. Now this point, maybe I drew it too far over. Here, let me make this v a little bit bigger. It's difficult to redraw let me make this v look a little bit longer. Imagine, this is not 100% scale. There we go. Now that's the v. See, it's like I took this point and I translated it over by v. And then I did the same thing with every other point in u. Just translate it over. Shift it by a little bit. Okay. Terrible drawing, but hopefully that makes it a little bit clearer. You're just moving it over by a vector. There's a really nice way you can do this, just in general. So this is the idea of this is best, I think, illustrated not by the example with a squiggly blob, though I think that illustrates it pretty well. Let's suppose instead now that we have a subspace. So here's the idea. Now, let's suppose that we have a subspace. Okay, in R2, subspaces that aren't all of R2 or trivial look something like this. Okay, now I could grab some kind of a vector. Let's take a vector, say like this one. It's like, let's let that be v. Okay, now if I redraw, I'm going to try to get the same angle. There we go. Okay, here we go. Now this is v plus u with a subspace. Notice, this new thing is no longer a subspace since it doesn't pass through 0. It doesn't have the 0 vector in it. I've shifted everything over, including the 0 vector, since if u is a subspace, take some vector v, add it to everything in there. Well, one of the things you'll add it to is the 0 vector. So you'll get back v. V will definitely live in there. It'll be right here when you move it over. Okay. And then everything else just gets moved over by the same amount. All right. So this makes some sense of the idea of translating. That is, we're just shifting it side to side, or if you want to see it similarly, you're just kind of moving it up and down. There's no real difference there. But we're just moving it over by a vector. Okay. So a quotient space just takes this and it defines a nice notion of addition and scalar multiplication on it. So we take u, a subspace of v, then the quotient space, which we'll write v over u, like a quotient, it's the set of all translates of u. It is just the set of v plus u, where v is a vector in v. So, to visualize, this is kind of what we're looking at. Okay, so we'll grab ourselves a subspace. All right, let's call this guy U. And notice U is equal to 0 plus U, since 0 is a vector, and if you add it to everything in U, you just get U back. This is just U, okay. Now we can also take other things. Let's draw, oops, let me use my nice line tool again. So just parallel translates of this guy. Okay, now what does this look like? Well, if I took a vector here, okay, so let this be a V. This is little v plus U. Okay, but that's not the only vector that does it. I could also have taken a V that points, say, over here, right? And then I would just move over like that. Oh, okay. So let's call this W. This is equal to W plus U. Oh, okay. So some different vectors give the same things. In some sense, you can start to see that there are fewer things in this quotient space than there were in the original vector space, provided that U is not a trivial subspace. After all, if U is just the 0 vector, then V plus 0 is just V, right? So let's do a little bit more at this. Let's define the addition. Let's define the scalar multiplication. But to do that, we're going to have to prove some properties about putting together translates and how they work. That is, we'll have to see what goes on when you get the same kinds of situations like this, when V plus W, or when V and W give the same translate of a subspace U. All right, let's see what happens. Okay, here's the theorem we'll have to prove to say that scalar multiplication and addition, the way we want to do them on translates of subspaces, makes sense. So here's the idea of it. Okay, the gist. If V minus W is in a subspace U, then the translate by V of U is the same as the translate by W of U. And this is the same thing as saying that these two translates intersect non-trivially. Okay, let's start. First, suppose that V minus W is in U. Okay. If U is in U, then observe that, here's the idea, V plus U, that's equal to V plus U plus W minus W. Yeah, agree with that. You just added 0. Okay, well this is equal to W plus V minus W plus U. And hey, would you look at this? That thing is in U. So this is in W plus big U in that translate. So we took something in an arbitrary element in V plus big U, and we got something that was in W plus big U. So V plus big U is in W plus big U. Likewise, repeating the argument with V and W interchanged, W plus big U is contained in V plus big U. So we have shown V minus W in U implies that V plus U equals W plus U. Oh, okay. Nice. Now, suppose V plus U is equal to W plus U. Then, V plus U intersect W plus U is equal to, well, V plus U or W plus U. They're the same thing. and neither of those are the empty set. Oh, okay. So v plus u equals w plus u implies v plus u intersect w plus u is not equal to the empty set. Okay, so we've gone from here and we've shown this first one, then we've shown the second one. Now we're going to take this one and we're going to wrap it around to the beginning, and we've got everything. Since if you want to go from here to there, then instead I could just follow from here to here and back around to the beginning. Make sense? So if we just complete the circle, we're good to go. All right. Finally, suppose that v plus u intersect w plus u is not the empty set. All right, if this happens, what can we do? Well, then there exists some u1 and u2 in u such that v plus u1 equals w plus u2, right? Rearranging, this says v minus w is equal to u2 minus u1, which is in u. So v plus u intersect w plus u not being empty implies that v minus w is in u. Hey, that's the last thing. So we just went across. Our method of proof went boom, boom, and then finally it went whoosh back over here. Make that a nice long weird double arrow. Whew, boom. Okay, so you can get from any one to any of the other ones just by following a path. Nice, very cool. Okay, so we've got a well-defined sense of when two translates of u are the same. It happens when they intersect at all, that is, unless v plus u is equal to w plus u, the intersection is empty, since having the intersection non-empty implies that v plus u is equal to w plus u. And these guys are equal precisely when v minus w is an element of u. All right, cool. We'll draw a picture momentarily, but let's see how we can use this to make a subspace out of this quotient space. Okay, here's the idea. We'll define addition and scalar multiplication on v quotient u, that is the set of translates of u by vectors in v, in the following way. We'll take v plus u and w plus u to be the translate by v plus w of u. So when I translate u by v and I translate u by w, I will add those two things together to get a translation of u by v plus w. And similarly, when I scale by lambda, a translation of u by v, I will just instead translate u by lambda v. Okay, cool. Nothing too crazy, nothing too weird so far. Let's see if this makes sense. That is, let's see if this is a vector space. All right, so we'll suppose that u is a subspace of v, and then what we're going to claim is that this set of translates of u with the operations of addition and scalar multiplication as we just defined is a vector space. So here's the idea. What we want to make sure of is the following. So the problem we want to show does not happen is the following. Okay, here's the idea. If v1 plus u is equal to v2 plus u, and w1 plus u is equal to w2 plus u, then could we get the following? That is v1 plus w1 u not equal to v2 plus w2, translating u. So we want to show that this doesn't happen. So this never happens. Okay, here, let me explain this a little bit more first. So the idea, as we saw a couple pages ago when I was trying to sketch this, is that, look, different vectors v and w can give the same translate of u. Okay, so what we don't want is we don't want our addition here to depend on which one of those non-unique vectors we chose when we wrote the translate of u. After all, the translate of u here, where I translated it by w and where I translated it by v, they are the same. It doesn't matter whether I use v or w, so it shouldn't matter when I'm doing addition whether I used v or w. That is, it shouldn't matter which representative vector I chose to describe how u was translated. I should get the same thing out when I sum together. Okay, so let's show that this never happens. Here's the idea. Now, okay, suppose that we have v1 plus u equals v2 plus u, and w1 plus u equals w2 plus u. All right. Then we know the following. Okay, from this, we immediately get that v1 minus v2 is in u, and w1 minus w2 is in u. Okay, cool. Now, this says, since u, not w, is a subspace, that v1 minus v2 plus w1 minus w2, I'm putting parentheses just to make it clear, is also in u. That is, I'm just adding together two things in u. Okay, so this says that v1, and now I'm going to rewrite it a little bit. Okay, v1 plus w1, that is this guy plus this guy, minus v2 plus w2, that is, I'm just factoring out that minus sign here, is in u as well. I just rewrote this. But we just showed that this implies that v1 plus w1, translating u, is equal to v2 plus w2, translating u. Oh, okay, cool. So addition makes sense. Nice, okay. Likewise, let's do scalar multiplication. Though I think this one is a lot easier. Okay. Likewise, let's suppose that lambda is a field element. Okay. And v1 plus u is equal to v2 plus u. Okay. Since u is a subspace, is closed under scaling, So v1 minus v2 in u implies that lambda v1 minus v2 is in u. Oh, okay. Hence, notice lambda v1 minus lambda v2 is in u. And so you see how we got this first part, v1 plus u is equal to v2 plus u? We just went through and proved that if that happens, then v1 minus v2 is in u. Okay, so we used that piece right here to get this piece. And now we're going to use it in the other direction to get that lambda v1 plus u is equal to lambda v2 plus u. So scalar multiplication makes sense. Okay, nice. That is, our representative vectors describing the translation do not influence the scaling or the addition. We can choose whatever representatives we want. That is, if you have v1 as a potential representative as well as v2, and you've got w1 as well as w2 as potential representatives for another translate, then it doesn't matter which ones you add. Do it however you want. You just take one representative from the first translate and one representative from the second, sum them together. That is a valid representation for the new vector translating u when you add together these two translates in the way that we have described up here. All right, cool. I'll say with this, the rest is routine exercise. I might make you do this, perhaps on homework or something like that. All right, cool. So scalar multiplication, addition makes sense. After you've got that, everything else is just checking some vector space properties. Nothing too crazy at all. All right, sweet. Let's see what we can get from the quotient the same way we got some stuff from products. Okay, quotient spaces maybe seem kind of confusing so far, at least when you start working with all these representative elements for translates and stuff like that. But actually, they're pretty nice. So let's talk about the quotient map. So if you've got a subspace U of a vector space V, the quotient map, which we'll write as pi, sends V to the set of translates of U in V by sending a vector V to the translate of U by V for each vector V in V. The claim I'm going to make is that if V is a finite dimensional vector space and U is a subspace of V, so finite dimensionality matters here quite a bit, then the dimension of the quotient space is the dimension of V minus the dimension of U. All right, cool. Here's the idea. So I claim this is actually super easy to see once we get into it. So let pi be the quotient map. Then, since pi of V is equal to V plus U, and V quotient U is just the set of V's plus U for vectors V in V, pi is surjective. That is, it just spits out a translate of U by V for each vector V in V, and that is all of the elements in the quotient space. Okay, nothing crazy at all. All right. Now, notice that pi of V is equal to 0 plus U, i.e., I'll write it this way. I'll say V is in the null space of pi, since 0, translating by 0, that's the additive identity, right? Okay. Since, you have to send 0 to the additive identity of any other vector space if you use a linear map. And if you send it in this way, well, that's what you get. Okay, so cool. This says the following. So if pi v is equal to this, then v plus u is equal to 0 plus u, which means v, which is equal to v minus 0, must be an element of u. So the null space of pi is just u. Okay. By the fundamental theorem of, you know, write the O small, of linear maps, dim v is equal to dim range pi plus dim null pi. Normally I write that in the other direction, but it's the same thing. We're summing, which says that dim v is equal to dim v mod u, v quotient u, plus dim u. Rearranging a little bit, this says that the dimension of v quotient u is equal to the dimension of v minus the dimension of u. Hey, that's what we wanted to show. Super easy. All right, let's keep going. All right, the last thing we're going to do with quotient spaces is a cool little trick that lets you understand linear maps a lot better. So here's the idea. We'll take a linear map from v to w, and we'll define its the special version of it. So we'll call it t, and then we'll define this new map, t tilde, to be a map from the quotient space of v by the null space of t to w in the following way. T tilde will take the translate of the null space of t by a vector v to just be tv. Notice, this makes sense. Here's why. Okay, so if v plus null t equals u plus null t, then v minus u is in null t, and t of v minus u is equal to 0, i.e., using linearity, t of v equals t of u. So if v plus null t equals u plus null t, t tilde of v plus null t equals tv, which is equal to tu, as we showed right here, which is just t tilde of u plus null t. Okay, that is t tilde does not depend on the choice of v used to represent v plus null t. Okay, cool. It shouldn't, because otherwise we'd be sending the same thing to different things, which would make this not even a function, right? Okay, so this makes sense that it is a linear map is very straightforward to show. It is as nice as you want it to be. It is a good little exercise if you don't buy it, but it works out super easily. So here's why we care about this guy. All right, if t is a linear map from v to w, then we're going to prove some facts. First off, t tilde composed with the quotient map is just t. That is, you can factor t as t tilde and a quotient. T tilde is injective. The range of t tilde is the same as the range of t. And this says, finally, that v quotient by null t is isomorphic to the range of t. That's actually kind of sweet. It says for linear maps, if you want to understand what they go to, what stuff you get out, you only have to understand what stuff they send to 0. So if you want to know what the range of a linear map is, just find out what it sends to 0. Then take the domain and quotient by that subspace. That is isomorphic to the range. That is a very powerful tool. All right, let's prove this because that tool will give us a whole lot of sweet stuff. All right, first off, part A. All right, if V is in V, then T tilde composed with pi of V, well, this is just T tilde of pi V. But what is pi of V if pi is the quotient map? Well, if pi is the quotient map sending, let me clear here. Pi is the quotient map, sends V to V quotient by null T, just to be clear. So this is T tilde of V plus null T. That is the translate of null T by V. But T tilde of this is just T V. Hey. So, since this works for any old V, T tilde composed with pi is equal to T. They agree at every single V, which is everything in their domain. They're the same map. Sweet. Okay. Injectivity. All right. Suppose T tilde of V is equal to T tilde of U. Or I shouldn't say of, I should write this more precisely because T tilde doesn't take V's and U's. It takes a V plus a null space of T. And it takes a U plus a null space of T. Writing a bit too quickly. Okay, so suppose T tilde of some element of the quotient space is equal to T tilde of some other element. Then, so we showed here that in this case, so we'll get TV and TU are equal, which means that we'll just reverse the argument. So then TV equals TU, which implies that T of V minus U is equal to 0, which says that V minus U is in null T. And this says the following. Okay, so we've got V minus U in the null space of T. All right, now we can use a nice fact from this. Okay. V plus null T equals 0 plus null T. Yeah, agree with this? And similarly, U plus null T equals 0 plus null T. Okay. So, well, here, maybe I want to do this slightly differently. Let me present a slightly different, shorter version of this. I'm just thinking through it and going, wait a second, there's a faster and easier way to do this. And I'm doing it in a more complicated way. Here, we'll show injectivity in the following way. We show injectivity by showing, I'll use the fact that we can just show that the null space of T tilde is trivial, i.e., null T tilde is equal to, well, T tilde sends v mod null t to w. So the stuff that it sends to 0 will show is only equal to the 0 vector in the null space of t, which is 0 plus null t. Or in the 0 vector in v mod the null space of t, which is 0 plus the null space of t. Okay. So it only has the 0 of v quotient null t. Okay. So, suppose t tilde of v plus null t is equal to 0. Then, t of v is equal to 0, since t tilde of v plus null t is defined to be t of v. So, v is in the null space of t, and v plus null t is equal to 0 plus null t. That is, since v minus 0 is in the null space of t. Oh, okay. Hence, t tilde is injective. That is, its null space is just 0 plus null t. Okay, cool. That's easier than the first way we tried to do it. We only have to do this argument once instead of doing it twice. Much easier. All right. Part C, we want to show that range t tilde and the range of t are the same. Let's just look up really quick. T tilde sends v plus null t to t of v. Okay. Do we get anything out? Do we lose anything? So, I claim that this is pretty much just the definition. So, if w is in the range of t, then there exists some v and v such that t of v equals w. So, t tilde of w plus null t is equal to t of not w, v. I'm writing too fast here. V, there we go. T tilde of v plus null t is t of v. It's the definition of t tilde, which is w, and w is in the range of t tilde as well. Write this argument in reverse to get w in range t whenever w is in the range of t tilde. Okay, so they're equal. Nice. Okay. D, I hope, is now maybe kind of clear. So from B and C, now B and C tell us t tilde is injective, and its range is equal to the range of t. Okay. So, I will write it this way. Well, here, even easier. I will say, from B and C, t tilde, if thought of, or I don't even want to say this because this is lazy. The map, I'll call it something else other than t. I'll call it R. How about R, which will define to be essentially the exact same as t tilde, but notice t tilde in our definition sends things to w. I will instead define it almost exactly the same, but replace w by the range of t. So t tilde from v mod null t, R from v quotient null t to range t, defined by R of V plus null t is equal to, I will just say, TV, since this gives us something in the range of t. This is the same as t tilde, but with a different codomain. So R is injective and surjective. Hence, it is an isomorphism. Oh, so V, quotient null t, and range of t are isomorphic. This might seem silly to do this R. That is, R is just t tilde, or R composed with the inclusion map of the range of t and w is equal to t tilde. But it's lazy to say that t tilde and R are the same thing. After all, surjectivity depends on what the codomain is. So t tilde may not be surjective, but R, which is just basically t tilde made surjective by replacing the codomain with the range, that thing is surjective. And this tells us that V, quotient by null t, and the range of t are isomorphic. Sweet. This is an isomorphism theorem, and quite a famous one at that. We will use it a lot in the weeks to come. But for now, I'll see you later. Have a good weekend.